Hi everyone, Senan this side, and in this video we are going to start our Doubly linked list playlist, in which first we will see insertion, and this insertion would be a three-part series, 3 for the theory, 3 for the implementation. And the way that we are going to go about this is, first we'll discuss insertion at head. In the next video we'll discuss insertion at tail, and after that we'll discuss insertion anywhere in between given the position. So that would be the idea. So let's get started. So first of all, we have to discuss why do we need a doubly linked list over singly linked list, right? If you remember, the singly linked list looks something like this. You would have a node, and the second part of the node would contain the location of the next node. So you don't have random access in this, and you have to do the traversal linearly. So that is the thing, and that does a lot of stuff for us. So why do we need a doubly linked list? So the reason is that in singly linked list, so if you reached this node, let's say for example, if you are at this node, there is no way for you to go back to this previous node. Now you want a data structure so that you can move ahead and come back without any issue, right? It should not be one way only. It should have bidirectional locomotion or bidirectional movement. So that is the reason why we require a doubly linked list. We won't go into a lot of detail, but you would see a classic example that your browser, the tabs that you open, the things that you search, the browser is implemented, or could be said that it is implemented as a doubly linked list. So if you use Chrome, on top you would have an arrows like this. So whenever you search something right on the screen or on Google, you would go to a web page. If you click that web page, you would go to somewhere else, right? And now if you press this back button from this new page, you come back to this page. If you press this again, you can go back to this page, the original Google search page. And if you press right, you would go here. So you can basically travel in this linear manner. That is one thing, but that's not we are discussing right here. So what is actually the node structure? So a node in a doubly linked list would look like something like this. It would have a data or the value, let's say, which is going to store the value, whatever we want to store at that node. For the moment, for this tutorial, we'll take integers as a classic example. Then what you have is something as a next pointer, which is same as singly linked list. Till here, it's exactly same as singly linked list. The thing that differs here is this, the previous. Let me change the ink type. So what is different here is this previous pointer. So this is exactly the same like singly linked list. It would hold the location to the next node, and this previous is an additional storage for storing the previous information, the parent information in a way. Not exactly, but yeah, you get the point. So your node would actually look like this logically, not actually, but logically. You would have a previous pointer, you would have a next pointer, and you would have a value. Now, if I draw it like this, it looks like a PN junction diode. That's a different topic in itself, but you get the point. You have the previous, you have the next, and you have the value stored at the node itself. Now, this is actually pointing to a different node previously. This is pointing to a next node, right? That is the idea. Now, let's understand insertion at head. So if you have to insert at head, what you need is the head of the linked list or head of the doubly linked list and the value that you need to store. And always when you have to do an insertion, you are adding a new node. Adding a new node, you should always have to allocate new memory for it, right? So let's take, for example, node star pointer, which is the new node, which is what? New, a keyword that allocates new memory, and the node initialized with this value that is given, right? This is a keyword in C++ that is for allocating new memory. So I'm trying to just give you a pseudocode. It's not exactly a C++ code. Okay, so that is about creating a new node. Now, how do you add this node to the head of the list? So let's discuss two cases, right? Case number one, what is this? When the list is empty. So when the list is empty, your node would be the first node itself. So what you have to do is make this as the first node, whatever node that you create, make this as the head, and then you return, right? Now the case 2 is where you have some list. It's not a null list. So let's draw and look at what doubly linked list looks like, right? So this node is this next pointer. It's actually pointing to the next node, and the previous pointer of this node is actually pointing to this node. And this is how the doubly linked list actually looks like logically, if you say. Similarly, this would be pointing to a next node like this, and this is actually pointing to this node. And if you ask about what would be the previous of this would be a null node, because there is no node previously. If let's say this is the list itself, what is the next node? Next node would be null. Now, what you would be given as this is the head already. So this was the case where your list is a null. This is the case where your list is not null, or it has some elements. So what do you do? So whenever you create a new node, right? Let's look at this. Let's say this is the new node that you created, and let me just copy this, copy and paste. Okay, so this is the idea. Let's say we already have an existing list. This is the head, right? And what you have to do is add this node to the list as well with this already existing list. So what you do, you take this and you need to point it to the next node. That's one, as well as you have to point this head back to this node, which is the same thing that we did in single linked list. But the only differentiating factor is that now in this head as well, we need to relink this node, this link basically. I need to relink this arrow to this. So first, when I create a new node, I need to link this node to this head. The previous of this current head of this previous original list should point to this new node. And after that, I can take the head and make it point to this newly created node. So that was case 1 and case 2. So let me just take this and let's just cut this. And so let's write the case 1. Let's say this is a comment which is not read by the code itself or the compiler. Comment case 1. So in case 1, you assume or you take that there is an empty list, and the way that you detect that is your head is actually equal to null. And if that is the case, what you do is you say this head is now this new node, and then you just return. That is the thing. Now, just so you know, whenever you initialize a new node, I'm assuming that your constructor would make this as a null pointer, make this as also a null pointer, and initializes the value that is given as a parameter to this constructor. So just keep that in mind. Otherwise, you also have to initialize that as well. Okay, that was case 1. Now case 2 is where there is a head which is a valid node, and you need to attach this node to the head of the list. So what you do is you take this new node, and new node's next pointer should point to what? The existing list, which is the head itself. Now this head's previous, which is this original head's previous, should point to this new node. Okay, what I'm trying to do is, when I have created this new node, I'm linking this to this head and heads previous to this node, and then I will just update the head. So now I can say that head is equal to new node, and if you want, you can just return the head and return head or void, whatever you want, depending on the implementation, because the way that I would be implementing this is through a class, and inside that class I would always have the access to this head, and that would be a private variable, so no person outside of this class could actually tamper with this head. So that is the thing. So this is case 2. So case 1, when you have a null list, you have an empty list, you take this head and assign this to the new node, and then you just return the head. Case 2 is where you have a valid list and you have to append an element into the head, before the head basically. So what you do is you take this new node and make its next pointer point to this head of this next list or the original list, and then you take the original list's head and mark its previous as this new node. So you have done this relinking of nodes, and after that, the head that was pointing here, you take this and point it here. So this is the reassigning of this new head, and then you return the head. So that is the problem. And yep, let me just properly end this function. So yeah, that's about insertion at head. What will be the time and space complexity. So you see, we are just allocating a single node. So I can say that my space complexity is actually order 1 constant. What is the time complexity? If you observe, there is no loops. All statements are constant time statements. So from that, I can conclude this is an order 1 operation for inserting at head. So yeah, that was the video. In the next video, we are going to discuss how to insert at tail in a doubly linked list. And after that, we'll try to insert at any given position. So that is going to be the most generalized case of this. So be sure to check that out. And eventually I will write the C++ implementation of this. So make sure to check that out. Anyways, thanks for watching, and I'll see you in the next video. Bye.